physics fans. I bet that you've been sad that Mrs. Cross and I've been gone for so long, but no worries, we're still here for you. Anyway, we are going to talk about rolling objects today. So the last few days we've been talking about torque, we've been talking about rotating objects. We're going to move on, still in chapter 8, talking about rolling objects. So I'm going to just put that down. You might want to write this stuff down too, because, you know, that's always good for you. So we've got rolling objects. And in just a minute, you're going to take a look at a demo, but let me kind of give you a setup, of what that demo is going to be. Hopefully this video won't be so crazy. So in front of you, you will see a ramp. You've seen ramps before, you know all about them. And there are going to be two objects. One is a disc made of wood, and the other is a ring, and they have the same mass. So the mass of the ring is equal to the mass of the disc. So in just a minute, those two objects are going to be rolled down the ramp at the same time, and I want you to think about conservation of energy, and I want you to make a prediction. I want you to write down on your paper the answer to the question, which object will reach the bottom first. And not only do I want you to answer that question, I also want you to write down why you think it's true. So I'm going to have you pause the video for a second and make that prediction, and then give it a shot. Okay, so hopefully you've done that. Hopefully you found out something, and maybe it surprised you. The masses are the same, but the two objects did not hit the ground at the same time, did they? No, no. If we look at it, looking at conservation of energy, which may have been the reason that you were thinking that they would hit the ground first, we know that the total energy at the beginning has to be the same as the total energy at the end, right? I mean, that's not a surprise. That's just conservation of energy. And if we talk about the kinds of energy that we have, we've got initial gravitational potential energy, and we've got maybe some kinetic energy at the beginning, but we know that that sum has to be the same as the total energy at the end. Okay, this should not surprise you. This is what, chapter 5 stuff or something like that. Okay, so this is nothing new, I hope. If we think about it at the very top, before the two objects were let go, their kinetic energy was 0. Would you agree? I hope so. You probably remember that we can set h equals 0 wherever we want, but we want to do it intelligently. So I'm thinking let's call h equals 0 at the bottom. That seems fairly logical, and that would give us a gravitational potential energy at the bottom of 0. So then if we go ahead and plug in our expressions for gravitational potential energy, mgh, and for kinetic energy, 1/2 mv squared, for either of these things, so we can either talk about the disk or the ring, you can see that we can find the velocity, right? The velocity would be, like, looks like the m's are going to cancel, something like this, 2gh. So it shouldn't matter which one's which. They should be the same. But we just did an experiment. We found out they weren't the same. So something has to be going on. So you may have passed those objects around so that you could see that they really do have the same mass. What is the difference between those two objects? The masses are the same, but there's something that's different. If you want to pause that and have a conversation, that'd be cool. Maybe in your conversation, you came up with the idea that while the masses are the same, it's the distribution of the mass that's different, okay? And the concept of distribution of mass is really important when we start talking about rotation. Okay, so really quickly, because I can and because I like to, you know, do things a little bit out of order, I'm going to make myself a little aside here. You may want to do this as well, just to remind ourselves of Newton's laws. Do you remember when we talked about Newton's law? Newton's first and second law. That was the one about objects accelerating. If I give the same force to two objects with different masses which one's going to accelerate more? What do you think? If I give the same force to two different masses, taking a look at F equals ma, hopefully it makes sense to you that the smaller mass, so I'll say m small, will result in a acceleration that is bigger. Does that make sense? The smaller the mass, the bigger the acceleration given the same force. Okay? This idea of mass in linear motion is what we're going to use to translate over to this idea of rotation. When an object is rotating, as it's going down that ramp, so if we take a look as this thing goes down the ramp, it's starting with an initial velocity of 0, and it's ending up with a velocity that's not 0, which means it is accelerating, right? Not only is there a force that has to cause it to accelerate in that straight line direction, it also has to start to rotate, okay? When an object is rotating, as we said, it's accelerating, and it's going to accelerate faster if the mass is more concentrated at the center. So the acceleration will be bigger with more mass at the center. So if we think about it's all rotating around that center. So if I have my disc, so this is that thing made out of wood, right? I've got my disc and I've got my ring. On my disc, I've got some mass that's way out here and kind of hard to get to move, but I've got some mass that's really, really close to the center and much easier to get to move around the center. Think about it in terms of torques, right? When we thought about torque, when we defined torque, we defined it as the force times the radius or the distance away, okay? It's going to be much easier to get something to move if it's closer to the center. Well, we've got these masses that are all kind of spread out in the disk. Those same masses have to be present on the ring, but those masses in the ring are really far apart, really far away from the center, okay? This thing here, this idea of the distribution of mass is what's going to cause the rotation to be different. This thing has a name. It's probably my least favorite named thing in all of physics. Are you ready for it? Here it comes. Just like the mass is the thing that affects straight line motion or straight line acceleration, this crazy term, here it comes, moment of inertia. What is that? Well, moment of inertia is the thing that affects rotational motion. So the bigger the moment of inertia, the harder it's going to be to get something to rotate. The smaller the moment of inertia, the easier it's going to be to get something to rotate. You're like, okay, great. You started rolling stuff down a ramp, and now you're talking about this crazy thing called moment of inertia. What do they have to do with each other? Well, let's take a look. So we've got these two objects. I couldn't draw this one back here because then you couldn't see it. But we've got those two objects that are rolling down the ramp. They're both going to be starting off with 0 velocity, and then they're going to go down the ramp. They're going to accelerate down the ramp. And in doing so, we're going to translate some of that gravitational potential energy into kinetic. Okay? Before I get too far into this to show you why that crazy disk beats the ring, I want you to take a look in your book at page 285. This is going to hopefully kind of help put together the reasons for all of this. So if you need to pause the video to grab books, go ahead and do that. But on page 285, you should see that there is a chart of all different kinds of objects being rotated about all different kinds of axes. And if you're going, that sounds absolutely crazy, don't freak out too much. It'll be okay. The thing that I want you to take a look at are these things called moments of inertia. It's marked with the letter I because that's logical, right? Marked with the letter I. I want you to look at the two that we're talking about, the hoop, okay, and the solid disk. Now this crazy thing I, this moment of inertia for the hoop, you'll notice is capital M, which is for mass, times r squared. And for the solid disk, capital I is equal to 1/2 m r squared. And if you're anything like me, when I first learned this, I'm like, well, that seems strange. I will tell you that all of these different things can be figured out with calculus. We're not going to do calculus today, but if you want to do it, come join me in AP Physics with calculus and we'll do it. It'll be fun, but not today. We're just going to trust it for now. Say, okay, that sounds good. Now let's get back to this conservation of energy business. So we know that the energy, I'm just going to write down what we knew before. The energy at the beginning has to equal the energy at the end. We got rid of this one because it's not moving. We got rid of this one because at the bottom, we're going to call that H equals 0. So we've got mgh is equal to the kinetic energy. Here's the secret that I didn't tell you before. As that disk rolls down the ramp, or the hoop rolls down the ramp, either way, it's got two kinds of kinetic energy. It's got the kind that we know and love, that 1/2 mv squared. No problem, we got that one. It's also got this thing that we call rotational kinetic energy. It looks kind of similar. It's 1/2 I, that's the moment of inertia, that crazy word that we talked about a minute ago, times omega squared. Now, if you've been doing any looking in the book, you may have seen this crazy letter omega. I don't want you to freak out about it. Let me tell you a little bit about this thing. So rotational kinetic energy is equal to 1/2 I omega squared. So I is whatever we have here, whatever we're going to plug in. And I'm just going to tell you this for now because we don't have lots of time to go over it. I'm just going to tell you that omega has to do with how fast something goes around in a circle. And omega is equal to v, the velocity, the tangential velocity, kind of like we talked about when we were doing circular motion earlier, okay, divided by r, the radius of the rotating thing. Again, there's a lot more to this, but for now I'm just going to ask that you say, okay, sounds reasonable. So say it with me. Okay, sounds reasonable. I couldn't hear you. I'm assuming you did it. If not, please go back and play it again and repeat it with me. Okay? All right. So now, how does this work? So which one won? Do you remember? Was it the hoop or the solid disk? The hoop or the solid disk? It was the disk, right? The disk won. And the way we would not be surprised that the disk won is if the velocity of the disk is bigger at the bottom. So we're going to go ahead and take a look at this. It's going to be a little bit ugly for a minute, but hopefully you'll be like, wow, that's kind of cool. So here we go. We're going to do this MGH business. I'm going to do this for the hoop first. MGH is equal to 1/2 mv squared plus 1, oops, that was a mistake. Let's see if I can get rid of that. Goodbye. There we go. 1/2 I is mr squared. I'm just going to plug it in so I don't have to look at that I anymore. Times omega, which is v over r, all squared. So hopefully that makes sense. Again, this is the translational kinetic energy, or the straight line kinetic energy, and this is the rotational kinetic energy, the energy as it's going in a circle. Okay, so that's what I've got, and now I'm going to try and figure out what the velocity is. I want to cancel stuff first because it's ugly. Let me get rid of these m's. M doesn't matter. Did you know that? M doesn't matter? Yeah, it cancels out. Look at that. So I've got GH on the left-hand side is equal to 1/2 v squared plus 1/2 hey, look, there's an r squared here, there's an r squared down here. That's pretty cool. Those are going to cancel. And I'm going to be left with v squared. So then this is going to be, oh, go away, please. I don't know why that's being so goofy. I don't really want you, clock. There it is. Sorry about that. So it's going to be GH is equal to v squared, because 1/2 plus 1/2 is 1, right? So v is equal to the square root of GH. That's a little bit different from what we found way up here. The velocity of the hoop, sorry, I had to double check to make sure I was speaking correctly, is going to be different than the velocity of something just sliding down the ramp. This is no longer correct. Not at all. It's going to be less fast. Okay? So that is the velocity for the hoop as it rolls down the ramp. But let's take a glance over here at what happens if we look at the disk. Sorry, lost my train of thought there for a second. All right, so we got mgh is equal to 1/2 mv squared. I know this is kind of ugly. I apologize, but I promise it's going to get kind of nice in just a second. 1/2. This is going to be, oops, let me go up just a little bit so you can see it again. I'm going to plug in my I, which is going to be 1/2 big M r squared times v over r squared. I realized that I had written my r as a little r here and a big R here when I was doing the last one. I hope that didn't freak you out. It's all the same radius. I was just getting lazy, so I apologize again. I don't want to freak anybody out. M's are going to go away, so I've got GH again on the left, same deal. I've got 1/2 v squared for that first term, plus, again, my r's are going to cancel. I've got 1/2 times 1/2, so that's 1/4. Oh, something a little different. Do we see this? So we've got GH equals 1/2 plus 1/4 is going to be 3/4 v squared. And if I solve that for v, looks like that's going to be the square root of what? 4/3 GH. The velocity is different. Do we see this? The velocity is different. By golly, that shouldn't surprise us, since this one won the race, right? It was going faster at the bottom, okay? It was moving faster for more time, so it's going to win. So there you go. That's why the disk won. Good show, huh? To kind of process this, get a sense of what's going on, I do have a problem for you to work on. So if you would turn in your books to page 297 and take a look at number 2. Go ahead and pause the video for a little bit and give that one a shot. I don't have the solution written out, but my guess is that if you put your brain power together, you should be able to figure it out. Once you're done, then push play again, and we'll talk about one more thing with one more super fun demo. Okay, one more super fun demo. As you've learned, we know that we like to conserve stuff, right? The two big things that we like to conserve, oops, let me move that down just a little bit more. There we go. Are conservation, well, I guess the things we want to conserve are energy, sorry. We just did that one. And conservation of momentum, right? So we realized just a moment or two ago that energy, while it is conserved, we have to take into account the rotation in order to make that an actually true statement. Hey, we have to do the same thing with momentum. Now, here's the thing about conservation of momentum. You see it all the time, especially during the Winter Olympics, okay? During the Winter Olympics, when you're watching figure skating, you observe the law of conservation of momentum for rotation all the time, okay? So I want to show you kind of what's going on, and then you're going to take a look at the demo. We know that linear momentum, the momentum from chapter 6 that we've done, know and love, P is equal to mv, we know that the momentum at the beginning and the momentum at the end have to be the same. Usually the only way that we can see that in an interesting way in physics is to crash stuff together, right? Like you take the two little carts and you crash them together and you observe the momentum at the beginning, the momentum at the end. We can also take a look now, though, at angular momentum. Angular momentum is marked with the letter L. I don't know why, but they liked it, so they called it L. And angular momentum is going to be defined kind of if we look carefully at what's going on here. The angular, or the rotational equivalent of M, is our very favorite and very famous moment of inertia. And our angular equivalent to velocity is that crazy thing that I didn't really tell you what it was, omega. Okay? If we look at this carefully, we translate this a little bit, we can call this I, and then I'm just going to write this as V over R because that's something we're more comfortable with. Okay? So angular momentum, this thing has to be conserved. It has to be conserved. It just does. I want you to take a look at a demo right now. This demo is super fun. You're going to have somebody volunteer, and that person is going to stand on a little turntable, okay? So here's my friend here. I don't know who's going to volunteer, but somebody great is going to volunteer. They're going to put their arms straight out. So there are their arms, there are their feet, and they have a smile on their face because exciting physics is going to happen, okay? I bet that you can predict what's going to happen as we do this, but I want you to think through it carefully. So that person is going to start spinning, 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 and then pull their arms in. Go ahead and write down a prediction. What do you think is going to happen? Once everybody has a prediction, maybe talk about it a little bit, and then give it a shot. So what happened? What happened? Did you notice that the velocity went up? They started spinning faster and faster as they pulled their arms in. If you put your arms out again, they slow down and speed up and slow down and speed up, just like the ice skaters do, the figure skaters do when they're spinning, 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 right? So the reason for that is that that angular momentum stuff, I, V squared, or V over R, has to be conserved. If we think about I as M R squared times V over R, okay, and this, that mr squared thing, that's the thing that can change depending on the type of object you have. But if we're just talking about that, it's like the mass, the big mass here and the big mass here. Maybe after I talk for a couple more seconds, you could try it again with some weights in your hands. It's really exciting then, okay? If you watch what happens there, as we pull their arms in, that means the radius is going to go down, right? And if L has to stay the same and the radius goes down, this thing turns into mr times v, by the way. If the radius goes down, the velocity has to go where? It has to go up. Whoa! Yay, conservation of angular momentum. It's so cool. All right. Hopefully that made a little sense. Give a problem a try. This is page 294, number 4. Hopefully today you can get those 2 problems figured out. And once you do, we'll be back shortly to go over them with you and answer the questions that you have. Hope that you have a great weekend, and we'll see you soon. Bye.